Greetings, real estate investors, to a strategic deep dive in our machine learning series. I'm excited to guide you through this episode, where we'll tackle a regression task using a classic dataset and a robust explainability tool. I'm working in Google Colab, walking you through each step clearly so you can follow along as we predict house prices in California. Let's begin by setting up our environment and gathering our tools for this investment-focused analysis. I start by installing the interpret library in Colab with a straightforward pip command. This library will enable us to explore explainable AI, helping us understand our model's decision-making process. Next, I import the necessary tools. NumPy for numerical operations, Pandas for data manipulation, and Sklearn's Fetch California housing function to access our dataset. From Sklearn, I also bring in train test split to split our data, random forest regressor for our model, and our square score and mean squared error to evaluate performance. From interpret, I import Morris sensitivity from the black box module, our tool for global explanations, along with the show function to display results. I set up inline visualizations with set visualize provider and inline provider, ensuring our plots render directly in Colab. I also set a random seed with NumPy's random seed set to 42 for reproducibility. With our tools ready, let's load the data. I load the California housing dataset using Sklearn's Fetch California housing function. I create a data frame with the feature names provided by the dataset. Medding for median income, house age, AVA rooms for average rooms, AVA bedrooms, population, AVA cup for average occupancy, latitude and longitude, and add the target column, which is the median house value in hundreds of thousands of dollars. I print the first few rows to examine the data. The first row shows Medinc 8.3252, house age 41.0, AVA rooms 6.984127, latitude 37.88, longitude minus 122.23, and target 4.526. That's $452,600. The next row has Medinc 8.3014, house age 21.0, and target 3.585, $358,500. This dataset includes 20,640 samples of California block groups from the 1990 census, with 8 features and a target ranging from 0.15 to 5.0, making it an excellent dataset for predicting house prices. Let's prepare the data for modeling. I split the dataset into features, and target X includes all columns except the target, the 8 features, and Y is the target, house value in hundreds of thousands. I use train test split to allocate 20% for testing and 80% for training, with random state 42, giving us 16,512 training samples and 4,128 test samples. The features are all numeric, and there are no missing values, so we're ready to train our model. I initialize a random forest regressor from Sklearn with 100 estimators and random state 42. Random forest regression is an ensemble method that constructs multiple decision trees, 100 in our case, each trained on a random subset of the data and features. It averages their predictions to reduce overfitting and improve accuracy, making it a strong choice for regression tasks like predicting house prices, where features like median income and location may have complex, nonlinear relationships with the target. I call fit on X-train and Y-train to train the model, allowing it to learn how features like Medinc and latitude influence house values. Once trained, I make predictions on X-test with predict, storing them in Y-pred, and evaluate with our square score and mean squared error. The results are impressive. Our square score is 0.8051 to 80.51% of the variance explained in the test set, a solid performance. Mean squared error 0.2554. Take the square root, about 0.505 or $50,500, which is reasonable for house values ranging from $15,000 to $500,000, though it suggests some error on high-value homes. I use Morris sensitivity from Interpret's black box module to explain our model's behavior globally. The Morris sensitivity method is an explainability tool that measures feature importance by perturbing inputs and observing how these changes affect the model's output. It uses a technique called the elementary effects method, where it varies one feature at a time across its range, calculates the change in prediction, the elementary effect, and repeats this process multiple times to estimate the mean effect, mu, and standard deviation, sigma, for each feature. A higher mean effect indicates greater importance, while a higher standard deviation suggests the feature's effect varies depending on other features, indicating interactions. I initialize Morris sensitivity with our model's predict function, xtrain as the background data, and the feature names from xcolumns. I generate a global explanation with explain global and visualize it with show. The output provides global feature importance scores, MEDINC 1.8873, the highest, indicating it's the most influential feature on house price predictions. Latitude 0.7886 and longitude 0.5675 follow, showing location plays a significant role. Ave Cup 0.4087, Avarooms 0.3871, and population 0.3792 have moderate influence, while House Age 0.2637 and Ave Bedroom 0.2325 have the least impact. These scores suggest that median income and location are the primary drivers of house prices, while features like the number of bedrooms have a smaller effect. The visualization likely shows a bar chart with MEDINC's bar towering at 1.8873, followed by latitude and longitude, with shorter bars for house age and Ave bedrooms, providing a clear ranking of feature importance. Let's dive deeper into these outputs. They're a goldmine for real estate insights. The first row showed a house with MEDINC 8.3252, house age 41.0, latitude 37.88, and target 4.526, $452, 600, while the next had MEDINC 8.3014 and target 3.585, $358, 500, suggesting high-income areas command higher prices. The R-square score of 0.8051 means our model explains 80.51% of the price variance, and the mean squared error of 0.2554 translates to an average error of $50,500. Decent, but with room for improvement on high-value homes. The Morris sensitivity results are particularly revealing. MEDINC at 1.8873 stands out as the dominant feature, aligning with the high MEDINC values in the head, 8.3252, 8.3014, corresponding to higher prices. Latitude 0.7886 and longitude 0.5675 indicate location is crucial. Values like latitude 37.88 and longitude minus 122.23 place these houses in the San Francisco Bay Area, a high-value region. Ave Cup 0.4087 suggests occupancy impacts price, possibly reflecting demand, while Avarooms 0.3871 and population 0.3792 show moderate effects. More rooms and population may indicate larger, more desirable homes. House age 0.2637 and Ave bedrooms 0.2325 being lower makes sense. Older houses, house age 41.0, 21.0, and bedroom counts, Ave bedrooms 1.02, 3810, very less in impact compared to income and location. Morris sensitivity's global view helps us prioritize features for investment decisions, highlighting income and location as key drivers. To conclude this real estate investment analysis, we've explored the California housing dataset, a 20,640 sample study of 1990s California block groups, and trained a random forest regressor, achieving our square score of 0.8051 and mean squared error of 0.2554. The global explanation via Morris sensitivity revealed MEDINC and location features like latitude as the top drivers of house prices, providing a clear ranking of feature importance. Random forest regression's ensemble approach captured complex housing patterns, and the Morris sensitivity method's perturbation-based analysis offered transparency for our black box model. Grab this code, experiment with feature subsets, and dive deeper into housing investments. I'm energized by this market analysis. Hope it's inspired you to explore data's role in real estate. See you next time for another strategic data journey.